All right, so I wanted to do a quick video on electrical safety. Safety is something that's extremely important. And obviously, we're speaking to people who are already in the trade or in trade school. And, you need to get your safety training elsewhere for sure. We're not an official OSHA training facility or anything, but I wanted to just cover some basics, some undisputed facts about electrical safety that you should know. If you're a training manager or something at a company, you can share this with your staff to just help get their mind in the game with electrical safety. So I'm going to do another video, particularly showing how to use a meter in a safe manner, some of the features of meter, but this is just general conversation. We're talking about the anatomy of electrocution, so specifically how you get electrocuted, which is killed from electricity, arc flash gear, PPE, lockout, tagout, fall risk, grounding and bonding, GFC and AFCI, and NFPA 70, the good old National Electrical Code. So we'll just go over this real quick. First is the anatomy of electrocution. So there's a lot of things that make a difference as far as if you're going to be killed, and a lot of it has to do with which direction it passes through your body. So if it goes, through your head and down through your foot here, that's very dangerous because it's traveling all the way down your spine and through your brain and also across your heart. So that's dangerous. Arm to arm is dangerous because from an arm-to-arm path travels across your heart or very nearby. Path is very important, but one thing that a lot of technicians say, it's kind of silly, is they'll say that it's not the voltage that kills you, it's the amperage. And while there is definitely truth to that, when we're talking about working on high voltage electrical systems that are connected all the way back to the main distribution panel, back to the transformer out at the street, you have nearly an unlimited source of amperage. If you get hit with a taser, it's true that you can get hit with very high voltages and not be injured, but that's because if you're hit with the taser is amperage limited. So it's a high voltage, but it limits the amperage. There's only so much amperage can travel through. But our bodies are a very resistive path. If you ever took a ohm meter and measured between your fingers and hand to hand, you would measure a very high ohm resistance, usually in the kilo ohm or mega ohm scale, which means that your body is generally going to, under normal voltage conditions, it's going to, conduct in these sort of milliamp ranges. And even at very low milliamps, you can, have enough of an electrical shock that it can electrocute you. Again, depending on the path that it takes. So there's a couple different factors to consider, and one of them is the path. But just remember that the amperage that's going to be drawn through your body is really a function of the power supply and whether or not it's limited or unlimited, and the voltage. And so at all of these amperage conditions, in most cases, the power supply in the building is going to be enough to supply that much amperage. The question just is how high is the voltage? This is, basic Ohm's law stuff. E equals I times R. So amperage is a function of the resistance more than anything else. So the voltage and the resistance, and your resistance is going to be fairly fixed. Some people are going to have varying levels of resistance. Obviously, if you're standing in a pool of water, that's going to reduce your resistance. From there, it's really a matter of the voltage, which is why it's far more dangerous to work with 480 volts than it is 120. All right, so anatomy of electrocution has to do with the voltage. So how high is the voltage? Power source, is it current limited or is it essentially unlimited? And when we work in a building where you are connected to the utility, you have essentially unlimited current available to you. The body is not going to draw enough current to trip a breaker, so it's just going to keep sitting there shocking you until one of you give up. Then it's the resistance matters. So are you standing in a pool of water? Are your hands moist? Are you wearing proper gloves, protection that's going to help increase that resistance to a point that you're not going to have a current flow? And what direction does the path take through your body? Does it go through your central nervous system? Obviously, if you have a short, from one finger to another on the same hand, it's not going to be nearly as dangerous as if it goes through your body, which is why experienced technicians, when they approach a panel, they usually approach it with the back of the hand. And so that way, if it is grounded in some way, it's going to cause the hand to grip away from the panel versus towards the panel. The safest place to get hit with a current is in the back of the hand. And then duration. Obviously, the longer that you're being shocked, the more likely you're going to be electrocuted. So to prevent electrocution, work only on safe voltages. 24 volts is generally considered to be safe if you're not without any significant PPE. When you get on higher voltages, though, you have to really think about increasing your resistance by making sure to wear proper gloves, rubber and leather gloves, make sure you're wearing proper work shoes, make sure that you have face shields, all that sort of stuff. We're going to talk about that later. And then think about the power source current. If you're connected to the utility, like we normally are on the stuff we work on in HVAC, that current is going to essentially be enough to fry you. It's going to just keep going until you're fried. The only exceptions to that would be things, like I said, like a taser, very high voltage and little pulses, maybe an electronic air cleaner, but it's not enough to severely injure you, at least not normally, because the current is limited because it's powered by a battery. So the amount of current is limited. Whereas whereas when you're connected to a utility, it's just going to keep going. Now, be very careful about the path that it can take, so make sure that your body is ungrounded, and obviously duration. You don't want to be alone where you could potentially be shocked for a long time. This is a handout from the American Electrician's Handbook from the 1920s. This is a real picture from a book that I actually own. I mean, this just shows you how much has changed. These guys were brilliant when it came to the engineering of electrical, but this shows the type of bravado that gets people killed. It says electricians often test circuits for the presence of voltage by touching the conductors with the fingers. This method is safe where the voltage does not exceed 250. We're talking 250 volts they were testing with their fingers back in the 20s, and is often very convenient for locating a blown out fuse or for ascertaining whether or not a circuit is alive. Some men can endure the electric shock that results without discomfort, whereas others cannot. And the next page goes on to talk about testing low voltages on your tongue, standing in water. I mean, it's crazy. This is before meters were common, but it just shows you how much has changed and how much more safe we've gotten in our mindset about working with electrical, because this is nuts. Don't do this. The next thing is we think about getting shocked or electrocuted as being the most dangerous thing, but arc flash is extremely dangerous. Anytime you get into larger commercial and industrial applications, it becomes very important that you are aware of the voltages that you're around, that you are aware of the devices, any open switch gear, because again, while the goal is to always only work on unenergized equipment, when you deal with large panels like this, you may be working on an unenergized circuit, but you may have an energized circuit very near. Arc flashes occur whenever there's a bridge, some sort of electrical bridge where an arc can flash across. And the higher the voltage is, the higher the risk is of arc flash. It's something you definitely need to be aware of. When you think about arc flash boundary, you want to be really careful about getting no closer to the equipment than you need to unless you're wearing your full appropriate PPE. And I'm not going to go fully into what sort of PPE you need to wear, but just be aware that when you're working in industrial and commercial environments, including air conditioning systems, pulling panels off of higher voltage air conditioning systems, you need to make sure that as you approach, you are properly covered with your personal protective equipment, which is what PPE stands for. There's all sorts of different categories of PPE, all the way from the very basics. No matter what you're working on, you should be wearing safety glasses and gloves, protective clothing, long pants, proper work boots that are well insulated, leather type work boots, all the way up to category 4, where you're wearing the balaclava and the face shield and the high calorie absorption, arc rating of clothing. This would be the most extreme, highest voltage applications. But in a lot of cases, working on, high voltage switch gear in a commercial and industrial environment, you need to be in this category 2 or category 3 range. Again, I'm not going to cover all the specifics, but it's good for you to be aware that this exists. And one of the most important things to have on your truck if you're doing electrical work is a lockout tagout kit. This is true of almost every segment of the industry. I don't care if you're residential, commercial, because for example, even in residential, you may do multifamily where you have to go between floors and you have to work on equipment that you're shutting off where you're not line of sight to the disconnect. And what a lockout tagout setup does is it allows you to independently lock a piece of equipment off at the disconnect so that you're the only one with the key who can unlock it to turn it on. And you can potentially put multiple locks in the lockout tagout lock. So that way, if more than one person is potentially working on the equipment, you're all going to be protected. Everybody has to unlock it before the equipment can be turned on. It's very, very important, very practical. Certainly not, as some people think it's overkill, but it is definitely not. In a lot of cases, you're shutting off units at disconnects that are well away from where you're working, especially if you're working past the disconnect side. So say you're removing a rooftop unit or doing significant work, maybe to a disconnect on a rooftop unit. You have to definitely make sure that it's locked out and tagged out so that somebody's not going to accidentally come along and turn it on. Another thing to consider with electrical, a lot of the deaths associated with electrical are simple shocks that then result in falling. And so you always need to be, properly tied off whenever you're working above 6 feet, according to OSHA. Again, I'm not going to get into all the specifics, but this is especially true when you're working on electrical because the odds that you're going to fall or increase when you're working with electrical circuits when you could potentially be shocked and fall backwards. Again, our goal is never to work on live circuits, but in many cases, some of those things may be out of our control. You may have some other live circuits that are adjacent to where you're working and your shock risk increases. And so when your shock risk increases, if you're working off of a ladder on a roof, then your fall risk also increases. You need to be aware of that. And so it's very important whenever you're wiring up anything to make sure that it's properly grounded, properly bonded throughout the structure, but also keep in mind that in some cases when you're dealing, especially with convenience outlets, anything where there's potential moisture involved, ground fault circuit interrupter, GFCI, is important because like we mentioned, you could potentially be a ground one path and not draw enough amperage to trip a breaker. And so a GFCI basically looks for imbalance between neutral and the hot. Again, this is for 120 volt circuits primarily. Convenience outlets is where you're going to see this more than anything else. But it's important to understand what they do and why they matter. And this is important when you're working with, extension cords and that sort of thing, which comes up a lot in the trade. GFCIs really will help protect you because, again, like I said, you can create a path to ground where it's enough to electrocute you, but it's not enough to trip a breaker. GFCI, by monitoring the difference between what's going in and going out, and if it sees an imbalance, then it knows that there's some leakage to ground and it can trip. Arc fault's a newer thing. I just don't want you to confuse it with GFCI. Arc fault actually uses a circuit board inside the breaker that looks at the potential or the possibility of arcs. And so if it sees a signal or a signature that looks like that there's an arc in the circuit, then that will trip the breaker. That's more for bedrooms, that sort of thing, to help prevent fires. So, GFCI is there to help protect you from being shocked or electrocuted. AFCI is there to help prevent things from burning down. So sort of different functions. And then finally, all electrical installations should be made according to the NEC, National Electrical Code, which is also known as NFPA 70. That's the National Fire Protection Association Standard 70. That's the Bible for proper electrical installations. And their goal, of course, is to prevent people from getting electrocuted, prevent fires, and then also prevent arc flash. But arc flash is more so covered by OSHA. So finally, let's just kind of sum it up. You got to be really careful about not working on energized circuits. You want to make sure to wear proper PPE. That's things like gloves, face shields, proper leather shoes, things like that to prevent you from getting shocked. Make sure that you understand that you could have a shock that would be well enough to kill you that's not necessarily going to trip a breaker, and use all the best practices to prevent yourself from being injured. So that's the basics here today. Like I said, I'm going to do some more hands-on demonstrations to show you how to use electrical meters to help keep you safe. Hopefully you found that helpful. Thanks for watching.